All right, in this video, we're going to focus on the probability of items that have only two outcomes. So let's take a look at something that has two outcomes. So we're going to focus on those things that have only two outcomes. So one of them, the simplest one, is flipping a coin. Rolling a die. Even rolling dice. But in, say, flipping a coin, you would choose, say, heads. Well, when you flip the coin, either a head comes up or it doesn't. So there's only two outcomes there, heads or tails, in fact. Rolling a die. You choose one number. When the die is rolled, either that number comes up or it doesn't. Pick a card. Suppose you're interested in getting, I don't know, a queen out of the deck. When you pull a card from the deck, either you get a queen or you don't. So let's take a look at this. Pick a card, get a queen. Let's say get a heads. Get a 5. It really doesn't matter what it is. For the first one, the probability that you get heads is 1/2. For the second one, the probability that you get a 5, any number in fact, is 1/6. To get a queen, the probability of that is there's 4 queens out of 52. Now we're going to also want to keep track of the probability of failure. Each of the things that I wrote there is the probability of success. So failure doesn't necessarily mean a good or a bad thing. It just means the opposite of success. So the probability of a failure when you roll a die is 1 minus 1/2. The probability of failure when you roll a die is 1 minus 1/6. The probability of failure when you pulled that one card is 1 minus 4 out of 52. So each of these, we are going to want to create something called success and failure. So let's do an example with this. What is the probability of rolling a 5 with one roll of the die? So here we know the probability of success is P equals 1 out of 6. You know that you've only chosen one number out of 6 that are possible. The probability of rolling anything else is the probability of failure. So the probability of rolling anything but a 5 is 1 minus 1/6. And we call this is failure. So each time you do any of these problems, you're going to have to decide what is success and what is failure. So we'll typically do this. The lowercase p will equal the probability of success. Then 1 minus p equals the probability of failure. Let's say you play a game where you roll a die 5 times. What is the probability of getting an odd number on every roll? Well, here we're going to roll the die 5 times in a row. So we could look at this as roll 1, roll 2, roll 3, roll 4, and roll 5. So for the first roll, to get an odd number, the odd numbers from 1 to 6 are 1, 3, and 5. And the even numbers are 2, 4, and 6. So notice when you roll a die, the probability of getting an odd number on one roll is 1/2. So we'll take 1/2. And when you roll again, the next roll is not influenced by the previous roll. That's where the independence is coming in. We also have 1/2. In fact, it's 1/2 every single time you roll it. And we end up with, let me just call it P for the probability. So this is going to equal 1 over 2 to the 5th power, or 1 over 32. What is the probability of, let's call it the outcome? I want to roll a 6 twice, so 2 6s and then 3 3s. So what's the probability that I get 2 6s and 3 3s? Well, in that order. So we can do the same thing as before. We can do roll 1, roll 2, roll 3, roll 4, roll 5. So now the probability of getting a 6 on roll 1 is now 1/6. Roll 2 is independent, so it's still 1/6. The probability of getting a 3 is also 1/6. The probability of getting any single number on the roll of a die is 1/6. So we have here is 1 over 6 to the 5th power. Now 6 to the 5th, I'm going to need a little help with my calculator. 6, you can use, this is your caret, this is the exponent button, to the 5th, hit enter. So 1 over 7776. But now let me vary this. What is the probability of 2 6s and 3 3s? So notice this is a little different. I'm not saying that the 2 6s have to come up front. The 2 6s can occur anywhere. Similarly, the 3s can occur anywhere. So think of this. When I have this, I could get this. One possibility is 2 6s first, but then 3 3s. Another possibility is something like this. Or this, perhaps. If I had a way of counting all the possible ways of mixing up and arranging the 6s and 3s, then I could figure out the total or the size of the event. Well, if you notice, since I'm moving around 6s and 3s, I want all of the arrangements of the numbers 6, 6, 3, 3, 3. And we have that. The number of those arrangements is we have 5 factorial divided by 2 factorial times 3 factorial. What do? We have 2 6s, that's where the 2 factorial comes from, and 3 3s, that's where the 3 factorial comes from. Remember, when we were talking about the total number of arrangements where we had repeated letters, the formula went like that. We took 5 factorial, the total number of numbers, and that's the numerator, and then we looked for the repeats. So here 6 is repeated twice, that's why we have a 2 factorial. 3 is repeated 3 times, that's why we have a 3 factorial. And in fact, you know this creature. You know this creature as 5C2. Notice that any one arrangement has probability 1 over 6 to the 5th power. And there are a total of 5C2 of them. Thus, the probability of 2 6s and 3 5s is, so we're going to have 5C2 times 1 over 6 to the 5th. Roll a die 5 times. What is the probability of 2 6s? This is a slightly different question than the previous one. Before I said 2 6s and 3 3s. Here I'm saying 2 6s and the other 3 numbers can be anything else, including a 6, I suppose. So we want the probability, well, when I say 2 6s, I mean exactly 2 6s. So I take back what I said. The other numbers have to be something besides 6s. So one possibility is this. So we could say on the first roll we could have a 6. Like that. So we got a 6 on the first roll. And actually, let me put it here because I want to put the probability up there. So the probability of getting a 6 on any given roll is 1 out of 6. Now roll 2, let's say it's also a 6. Probability of that is 1 out of 6. Now the other ones all have to be not 6s. So let's just say not 6. Well, the probability of something not being 6 then is 1 minus 1/6. Not 6. Not 6. So what we get then is I'll get 1/6 raised to the 2nd power times 1 minus 1/6 to the 3rd power. Another possibility looks like this. So when I do my rolls, I'll have roll 1, roll 2, roll 3, roll 4, and roll 5. So here I could do a 6 on the first roll, and maybe I don't get a 6 until the 3rd roll. 6 on the first row is a 1/6. A not 6 then on the second row. The probability of that is 5/6. Then of course we see the probability of a 6 is 1/6. And then we have a not 6, and then a not 6. Now notice we have the same thing as before. Those 5/6 are the same as 1 minus 1/6. Let me take it out. I want it to fall into the same formula as I did before, because I'm really trying to show you how the formula kind of develops. Notice this probability is exactly the same as the previous one. You're going to get 1/6 raised to the second power times 1 minus 1/6 raised to the third power. So no matter what, the probability is always 1/6 to the second times 1 minus 1/6 to the third for each and every one of the 5C2 possibilities. Remember, we're doing 5C2 because we have a total of 5 items, and 2 of them are the ones of interest. Thus, the probability of 2 6s is, I take my 5C2 times 1/6 to the 2 times 1 minus 1/6 to the 3. Let my calculator do the business. I don't care about decimal. I think in this section we are asking for the decimals to be at least 4 decimals in length. That way, if you write it as a percentage, you'll have 2 decimal places of accuracy in percent form. Anyways, let's turn this thing on and put in my numbers. First thing I need to put in is the 5C2. So remember, you do 5, go up to math, go over to num, choose number 3, and then don't forget the 2 that's at the end of the thing. It's an annoying notation, but then I can do times, and then I could put parentheses, 1 divided by 6, finish that parenthesis. I can raise that to the second power, come down, start a new parenthesis, 1 minus 1 divided by 6, finish that parenthesis and raise to the third power, hit enter, and let's see what we get. 0.1607. Let me do something here just to be safe. I'm going to come back up here. I'm keeping this in the video because I want you to see. Your calculator sometimes will attempt to make you get a wrong answer, and I want to try to prevent that. To be on the safe side, I think you should put the 5NCR2 in parentheses. So I'm going to put a parenthesis in front of it. The reason why I suggest that is because I don't know for sure whether it's going to multiply 2 times all that stuff and then try to do the NCR thing. So let me change this and put a parenthesis. Now if I get the exact same answer, I'll feel comfortable that it's the right one. And it does. So the calculator does know how to work that. So we get about 0.1608. Let's continue with some more questions. What is the probability of 3 6s? So if I look at it this way, I could get something like 3 6s. I could have, this is one possible arrangement. I could have a 6, a 6, a 6. And then I could have a number that is not 6. Let's call it failure, F for failure. So each one of these, the probability of that 6 is 1/6, the probability of that 6 is 1/6, the probability of that 6 is 1/6, and the probability of each of those failures is 5/6. So each of these has a certain probability, and that is 1/6 raised to the third power times 5/6 raised to the second power. See, if you multiply all these, you get that. Additionally, if we look at this possible arrangement of numbers and letters, this can have a total of 5 factorial, because there's 5 objects here. 1, 2, 3, 4, 5. However, the 6 occurs 3 times and the F occurs twice. And if you recall, this is equal to 5C3. Therefore, the probability of 3 6s is, I'll take my 5C3 times 1/6 to the third power times 5/6 to the second power. Let me use the letter P to represent this probability. Now let me have my calculator. Now, one thing I've told you about that you can do is you can come back here and bring down that expression, and then all you have to do is change some things. Like for this, all I've got to do is make that exponent a 2, that exponent into a 3, and then I think I need to change that 2 to a 3, and I'm done. Here we have 0.322. Let me ask another question. What is the probability of getting 4 6s? Hopefully by now you can see the pattern here. We do 5C4, 1/6 to the fourth, times 1 minus 1/6 to the first power. Let's let our calculator crunch that. So let's see, I'll change that then to a 1. Although if you put nothing there, it assumes that it will be a 1. This one will be a 4. And then I need to make sure that that is a 4. Enter. I have 0032, approximately 0032. What is the probability of 5 6s? So all 6s. I should put my question marks here. So here now we are going to have 5C5 times 1/6 to the fifth times 1 minus 1/6 to the 0. By the way, just to show you, 5C5, that's going to equal 1. And anything not 0 raised to the 0 power is equal to 1. So this is just equal to 1 over 6 to the fifth. I don't care if you know that. You can just write this formula and you'll get the same thing. So we're going to do 1 divided by 6 raised to the fifth power, and we end up with 0.0013. Now, let me ask another type of a question here. What we did is we did for how many sixes? We did 3 sixes, and then I think I did 2 sixes. All right. So here's another question. What is the probability of 2 or more sixes? So what we have to look at is 2 or more sixes means that we have the probability of 2 sixes or 3 sixes or 4 sixes or 5 sixes. Now, when you roll these 5 die, or this die 5 times, it's not possible to get 2 sixes and 3 sixes. It simply cannot happen at the same time. So what I'm getting at is each of these, 5 outcomes is mutually exclusive. So what that means is I can rewrite it as the probability of 2 sixes plus the probability of 3 sixes plus the probability of 4 sixes plus the probability of 5 sixes. And we did each and every one of these. If you recall, this was 5c2 times 1/6 to the 2 times 1 minus 1/6 to the 3 plus 5c3 times 1/6 to the 3 times 1 minus 1/6 to the 2, 5c4, 1/6 to the 4th, 1 minus 1/6 to the 1st, and I'm running out of space, so I'll put it under here, plus 5c5 times 1/6 to the 5th, 1 minus 1/6 to the 0. And we'll go ahead and let our calculator do all those things. This is actually an approximation, so I'm going to change that to squiggle lines. And so all I need to do, that's one way to do it, and it's an exhausting way to do it. Another way is the following. We have the probability of 2 or more sixes equals 1 minus the probability of 1 or less sixes. So 2 or more, 2, 3, 4, 5, or 6, or 1, 2. 1, 2 is easy. This probability here, the probability of 1 or less sixes, that's the same as a probability of 0 sixes or 1 6. That's the probability of, let me see, 0 sixes, that'll be 5. Well, actually, let me just, I don't want to drop this step. That's the probability of 0 sixes plus the probability of 1 6. And now I'm ready for my probability. So I have 5c0, 0 sixes, 1/6 to the 0 power times 1 minus 1/6 to the 5th power plus 5c1 times 1/6 to the 1st power times 1 minus 1/6 to the 4th power. Now remember, I got to do 1 minus that. So the probability of 2 or more sixes equals 1 minus the previous answer that I got. That's the probability of 1 or less 6's. It's 1 minus 0.8038. And let's compare it to my previous answer, and you can see they are exactly the same. So making use of this, remember this is the probability of something not happening, sometimes can be very useful in saving you a lot of effort. Suppose you take a 10 question multiple choice exam and every question has 4 parts. So we could be looking at something like this. We could have A, B, C, D. If you guess on every question, what is the probability of getting 7 correct? So what we need to do is look at one particular possibility that can happen. I'm going to use the letter C for correct and W for wrong. So one desirable outcome is, so we would want 7 correct. So maybe the first 7 are correct, 2, 3, 4, 5, 6, 7, and then the last 3 are wrong. Well, if you look at this, the probability of any one answer being correct is 1 out of 4, because there's only 1 correct and 3 incorrect ones. 1 out of 4, 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 1 out of 4. Of course, you'd multiply those all together. Now, the probability of getting any one question wrong is 3/4, or 1 minus 1/4. So that's any one, or that's only one of all the possibilities. The total number of possibilities is, remember now, we have 10 objects, 10 factorial. The C is repeated 7 times, and the W is repeated 3 times. Thus, the probability of 7 correct equals 10C7 times 1/4 to the 7th. That's the 7 correct ones. And then 1 minus 1/4 to the 3rd. That is the 3 incorrect ones. And let me see what my calculator says for this. So we'll put, I like to put it in parentheses, 10 math PRB 3. Then don't forget to put your 7 and the parenthesis, although I know we don't have to do that. Now let me do 1/4, put a parenthesis, and that's raised to the 7th power. And then we put a parenthesis, 1 minus 1/4. Don't forget to put the division here. finish that parenthesis, and we want that raised to the third power. Enter. And we have 0.0031 approximately. All right, and you can play the same game. What is the probability of 8 correct? So here, the probability of 8 correct equals 10C8 times 1/4 to the 8th times 1 minus 1/4 to the 2nd. So I'll go up and grab the previous one and edit it. So I want a 2 up there. And I want an 8 up there. What else do we need? 10C8. Enter. This will be 0.00039. While we're at it, what's the probability of 9 correct? That's going to be 10C9 times 1/4 to the 9th times 1 minus 1/4 to the 1st. And let's go ahead and have the calculator do that. So that now is going to become a 1. That will become a 9. And then I have 10C9 to begin the thing. This, now I have 4 zeros before a 286. 0.1234286. I'll check those decimals one last time. 286, yep. And as you can imagine, I'm going to ask you, what's the probability of getting all 10 correct? So that is going to be 10C10 times 1/4 to the 10th times 1 minus 1/4 to the 0. And remember what I told you before. 10C10 is equal to 1. 1 minus 1/4 to the 0 is also equal to 1. This has the lowest possible probability of happening because you're taking 1/4 to the highest possible power that you can, and that's the smallest decimal of all of them. So anytime you take a decimal that is between 0 and 1 and you raise it to higher powers, the number gets smaller and smaller. Anyways, I'll let my calculator do this one. So let me go back up there and grab my things again. And this time we want a 0 in that spot. We want a 10 up there. I think this is okay. It'll stay up there and overwrite the 9. And then I need 10C10. So once again, I'm going to put a 1, but I need to insert the 0 so that it works right. Enter. Now this is a super low. That E-7 means there are 6 zeros before you have the 954. So we have 0.12345, zeros, 954. I mean, you could round to 6 decimal places or whatever. I just want to have enough decimals to see the numbers. So what we've calculated is 7 or more correct. What is the probability of passing? That would be 7 or more correct. So we would have the probability of 7 correct, or 8 correct, or 9 correct, or 10 correct. Of course, once again, these are mutually exclusive outcomes, so you can't have a 7 and an 8 at the same time, for example. So I can break this up into the probability of 7 correct plus the probability of 8 correct plus the probability of 9 correct plus the probability of 10 correct. Now, I'm not going to go ahead and write all those numbers down. I'm going to take my calculator and do it for me. So you got to be careful here. I've noticed that when you enter things without thought, it can cause a lot of issues. So let me go way up to the 10C7, like so, and I'm going to put a plus after it. So I have the probability of 7 correct. Now let me go up and find the probability of 8 correct, which there it is. And I believe I've added that on, so let's put a plus after that. Now let me go up and find 9 correct. There it is. And let me put a plus after that. And then 10 correct. And then hit enter, because I'm adding them all up. So here I have about 0.0035. Or as a percent, 0.35% probability of passing the course, of passing the exam. What is the probability of failing the exam? Well, that would be 6 or fewer correct, or you could simply do this. The probability of failure equals 1 minus the probability of pass. So 1 minus 0.0035. And you don't have to do that even. You can come here back to your calculator, and I can do 1 minus, and if you want, just go up there, enter, and then enter again, and we get about 9965. Or 99.65% chance that you'll fail the quiz. So some of the things that we've talked about that are binomial trials, if you will, roll a die. You know, either your number comes up or it doesn't. Flip a coin. So over there, if you wanted heads, H either comes up or it doesn't. What would be another one? Well, answer one of these questions by guessing. For each question, you're either correct or not. So you can see each trial is binomial in the sense that you have two possible outcomes. Now, in the case of flipping a coin, each of the outcomes that you can have is the same, same probability. Probability of heads or tails is the same. But rolling a die or possible multiple choice questions, not so. You still have two possible outcomes, either correct or not correct, or your number either comes up or it doesn't come up. But the probability of success was smaller than the probability of failure in those problems. So what we need is this. We were doing binomial trials. So for each binomial trial, let's see some of the things that we needed. Each trial has exactly 2 outcomes. And we have called these success or failure. So either one of those 2 outcomes is always possible. Subsequent trials are independent. Well, so rolling a die, for example, I get a certain number, but when I roll the die again, whatever I got on the first roll, it doesn't matter on the second roll. The next roll is independent. It has no idea what I got on the first roll. So we need that independence for all this stuff to work. The probability of success is the same for each trial. So if I'm rolling a die and I'm interested in the number 6 coming up, then the probability of success is 1/6 because I'm choosing just one number out of 6 possible. And every single time I roll that, I have exactly a 1/6 chance of success. So we need the same probability of success each and every time. And then it's repeatable. So all the examples I gave you are binomial examples. So let's go ahead and get the probability then. So the probability of k successes, that should be an NCK, times whatever the probability of success is raised to the k power, and then 1 minus p raised to the n minus k power. So n equals the number of trials lowercase p is the probability of success, so now this extremely powerful formula can be used. As long as you can recognize it's a binomial experiment, you can go right to this formula. All right, here I want to do a few of the problems from the textbook. I'll do the even numbered ones here. You're selecting a card and you look at it and you put it back in the deck. The deck is shuffled and you pick the card again. The process is performed a total of 5 times, each time you're shuffling in between. So what we have here are 5 independent trials since you're putting the card back and shuffling again. Now we're talking about the probability of getting various numbers of queens in all of this. Well, let's start with the probability of success. So when you pull a single card, the probability it is a queen is, I'm going to call this lowercase p because I'm going to use it as my probability of success. There are 4 queens in a deck of 52 cards, so my probability of success is 4 out of 52. Now let's take a look here. We're doing this 5 times, so n equals 5. The probability of getting exactly 1 queen, that means k equals 1. So our capital P, I'll use capital P for probability. 5 trials, 1 success. Success is 4 out of 52. And I raise that to the 1, and then I do 1 minus 4 out of 52. And I raise that to the 4. You've probably, hopefully you noticed that this exponent plus this exponent always equals n. So I get this number. Let me go ahead and let my calculator do it. Let me cordon this off so I don't run into it. I think I'm going to start a whole new one now. I like parentheses around my 5C, so I'm going to put 5. Let me get to my math, PRB. Then I want number 3. For this problem, I want a 1, so let me put a 1. Finish the parenthesis. And now we're going to do 4 divided by 52. And I'm going to raise that to the first power. Not necessary, but I'm doing it for display purposes. Times 1 minus. I got to be careful, I use my keyboard instead of this thing. 1 minus 4 divided by 52. And that's raised to the 4th power. Hit enter. So 2792. All right, let me move on to 3 queens. K equals 3. Then P will equal 5C3 times 4 over 52 to the 3 times 1 minus 4 out of 52 to the 2. And this will be easy because all I need to do is come right back up here, just edit this guy. This thing now up here will be a 2. This thing up here will be a what? A 3. And then I have 5C3 on the front. Here I get about a 0.0039. What is the probability of getting 5 queens? So K is equal to 5 here. So P will equal 5C5 times 4 over 52 to the 5th power times 1 minus 4 over 52 to the 0 power. And you can see this will be our smallest possible percentage because this last piece is 1, this first piece is 1, and we're taking a very small number and raising it to the 5th power. So anyways, I'll grab the same look expression from before, and I'm going to have a 0 up on that exponent, and then I'm going to have a 5 up there, and 5C5, enter. And that -6 means I have 5 zeros before I get to that 2. So I'm going to say 5 zeros 269. 0.0000269. Alright, a similar problem as the one I have before. The probability of getting the flu in any given year is 38%. So my probability of success, if you will, that is getting the flu, is lowercase p equals 0.38. Now, we're considering a 5-year span. So that 5-year means that n is equal to 5. So let's take a look at number 28, the probability of getting flu in any one given year. So here we have k is equal to 1. So our capital P probability is 5C1 times 0.38 to the 1 times 1 minus 0.38 to the 4. And you know, while I'm here, I'm going to do the even ones anyways. K equals 3. P equals 5C3 times 0.38 to the 3 times 1 minus 0.38 to the second. Here I'll do number 32. K equals 5. P equals 5C5 times 0.38 to the 5th times 1 minus 0.38 to the 0. I'll go ahead and calculate them now. I'll start a new one of these. 5 math PRB number 3. I'm doing this first one, so I'm going to put a 1. Finish that parenthesis. Then we have times. I'm not sure you need the times, but we have 0.38, and I'm going to raise that to the first power. And then I know you don't need a parenthesis here. Then I'm going to do 1 minus 0.38. Let me finish that parenthesis. And I'm going to raise that to the fourth power. And let's see what we do when I hit enter. Oh, it didn't like something. And as always, you have to be careful on your calculator. Hit the big minus and not the little one. So here I have about 2.2808. For the next one, all I have to do is edit my previous one. Here, now I want that exponent to be a 2. I want this exponent to be a 3. And then we have 5C3 at the beginning. And I have about 0.2109. And this last one, here we are going to have a 0 on that spot, then a 5 on that spot, and then we have 5C5, 0.0079. So that takes care of the more straightforward ones. Number 34 is a little bit different here. Now, 2 of the last 5 years, getting the flu in at least 2 of the last 5 years. So we need to look at k equals 2, or k equals 3, or k equals 4, or k equals 5. So for that then, let me do, we didn't do 2, did we? We didn't do 4 either. So I don't think it'll take much of a lot of work to do all that. So the probability of k equals 2, or k equals 3, or k equals 4, or k equals 5. That equals the probability of k equals 2, plus the probability of k equals 3, plus the probability of k equals 4, plus the probability of k equals 5. Well, for k equals 2, we have 5c2 times 0.38 to the second power times 1 minus 0.38 to the third power. K equals 3. I'll have 0.38 to the third power, then 1 minus 0.38 raised to the second power. Then k equals 4, 5c4 times 0.38 to the fourth times 1 minus 0.38 to the first. And then finally, plus 5c5 times 0.38 to the 5 times 1 minus 0.38 to the 0. Let me go ahead and let my calculator do all of this. I don't want to write up each of the numbers. So if I go up here, I did it for 1. So let me put a plus after this. And then I did it for 3. Now let me put a plus after that. And then I've already done it for 5. And let me put a plus after that. Now I did not do it for 2 and 4. So let me do it for 2. And what I'm going to do is just edit the 3 one. So with 2, I had a 3 in that spot, a 2 in that spot, and a 2 in that spot. So now I've got 1, 2, 3, and 5. I need 4. Plus, well, let me edit another one then. I'll grab the same one again. This will be my 4, and then I'll have to put a 1 here. I'll put a 4 here. And then I will put a 4 here. So let me come through and look at all of what I have just to make sure I didn't mess anything up here. Okay, the question was to have 2 or more correct. I don't know why I did the 1, so I'm going to delete the 1 out of there. Okay, so then I have for 3. Got that. Then I have for 5, so I have 3 and 5. Now I need 2 and 4. There looks like my 2. And then I need my 4. Come on, 4. All good. It looks like we got our 4. And nothing else, so I will hit enter. And I get about 0.6276. Or you can do it this way. Let me get that equals out of there. So let me put a big fat or here. The probability of 2 or more years equals 1 minus the probability of 1 or fewer years. That probability, the probability of 1 or fewer years, that equals the probability of k equals 0 or k equals 1. That's the probability of k equals 0 plus the probability of k equals 1. And we've done probably most of these. Here is 5c0 times 0.38 to the 0 times 1 minus 0.38 to the 5 plus 5c1 times 0.38 to the 1 times 1 minus 0.38 to the 4. Let's see, if I try to find 5c0, you've got to watch because a lot of these previous expressions added a lot of things together. I got to find the first place where I ever did a 5c0 or 5c1. There's 4 out of 52 is the previous problem. So I went, there it is right there. Let me enter that and see if it's just this. So that is 1. And then I'm going to plus, and let me grab that exact thing again. Just something that doesn't have a bunch of stuff attached to it. That looks like our guy again. This time, this is raised to the 4. Well, actually, no, I already did the one where I had 1 and 4. So now I want to do 5 and 0. Let me change that 1 to a 0 and then make sure we have this. The calculator is cumbersome to use in many applications here. So that's this part here. That's 5c1. And then I have 5c0.38 to the 0. All right, let's hit enter. It didn't like, I probably got a minus that it didn't like, so let me fix that. 0.3724. And then don't forget we want to do 1 minus that. So the probability of 2 or more years equals 1 minus the probability of 1 or fewer years. That equals 1 minus 0.3724. And once again, I'll let my calculator do this. I'll do 1 minus, go up and grab that number, hit enter again, and I get my 0.6276. And of course, that agrees with our earlier example. Our earlier answer.